Okay, and I see it's being recorded. So last time we stopped at the page number 21. So today we will look at introduction, a little behind today, but let's see how fast we can go today. We will try to spend the last hour on Simulink. Okay, as I mentioned to you already, Tirarat Pavi, have you worked on the MATLAB commands?
Yes.
Okay, so
Yeah.
okay, so during last hour today, we will look at Simulink, and from now on, during let's say last hour, 45 minutes to 1 hour, we'll go to Simulink only. Okay, okay, let's start then. So where did we stop the last time? So basically, so some of the slide maybe I go faster. Okay, yeah. So what is the communication system? In general, when we talk about the communication system, we talk about two parts. We have three parts. We have basically three components. Okay, one is the transmit side, transmitter, transmit, and channel, and then receiver. Okay, three parts. So the reason we have to look at this is because normally the channels is the one that has some restriction or have some constraints, like it has noise involved or it has limited bandwidth, maybe it has fading or some type of distortion additionally. Okay, so therefore we need to normally design the receiver so that on the right hand side we have a good performance in the system. And similarly, sometimes we try to design the transmit side as well to uh, follow or to have so that the data pulses have certain properties, that will conform to the channel, so that the receiver doesn't have to work so hard. Okay. So for digital communication system, basically we try to transmit data, whether in general, in whatever forms they come in, we will try to convert it into binary data first, binary data, okay. And from here, then we design some pulses to represent these binary bits. So the pulse, they come from finite set of possible pulses. If we talk about binary, it means we have two types of pulses. Okay, each pulse represents bits or symbol. Okay, we'll talk about symbol later, but first, for simplicity, let's talk about binary case first, which consists of 0 and 1. Okay, so when you transmit to the channels on the receive side, we have some receive signal with some distortion, you know, with noises, maybe the amplitudes also changes and all that. And the key idea is on the receive side in the digital system, we try to make decision. We try to make decision on the transmitted bits and symbols. This is different from the analog system. In analog system, um, okay, let me ask maybe briefly. Okay, Thirarat, what's the difference for analog system? What is the role of the receiver compared to digital system?
Um,
What is it trying to optimize or trying to achieve, or what is it trying to what type of performance it is trying to reach?
is try to receive the signal and decrease noise.
Exactly. So for analog system, you're trying to, if you decrease the noise, it means you want to increase what? We want to in analog system, it tries to optimize the SNR, right? Okay. It tries to optimize the SNR on the receive side. Or it also tries to decrease, eliminate some distortion. Distortion. Okay. Because in analog system, Thirarat Pavi, in analog system, it tries to reconstruct the transmitted pulse as close as possible to the original uh, information, the, the original information signals. Okay. On the other hand, for digital system, the goal is trying to reduce bit error rate. Okay. So along the process, maybe you try to optimize SNR, you try to decrease distortion as well. But at the end, the end goal is to reduce the bit error rate. Okay. Or if we talk about some type of non-binary system, we can talk about symbol error rate. Okay. Or you can talk about frame error rate. So at the end of the day, in digital communication system, we reduce this type of parameters. Okay. Does it have to reduce the bit error rate to be zero? Not necessarily. There's no need to make it zero, but it tries to reduce the bit error rate. Okay, corresponding to data type. I would say data types. Yeah, it's okay. Data types. If it's the voice, maybe you would reduce bit error rate to a certain level, and then it's okay. If you talk about images, you know, if you talk about images, maybe you reduce the error rate lower than the voice signals. Okay. And what are the existing digital communication standards nowadays? As you can see from this slide, there are so many. We can divide them into three types. One is the wired system, which is the communication system where you have to transmit through some wires or some fibers. Okay. Another type is called wireless system. For in this case, when you transmit data, you transmit through airs, you transmit through space, and so on. And the last part that people are not aware of, but it's also very important, is another type of digital communication standard related to data storage. Okay, so for what as an example for wired system, what are some of them? Maybe you talk about home telephones. Maybe at home you don't use so much these days, right? But maybe you don't use so much these days, but in offices they still use how do you call it, the office telephone, right? Then there are this type of home internet or office internet where it's based on ADSL. Most for ADSL we talk about transmission through telephone lines, but has very high data rate. Then you talk about power line communication, meaning that you transmit through the electric power lines. And some related standard is smart grid. Then you talk about optical fiber communication. These days, the home internet is based on optical fibers, right? That are operated and serviced by some of these telecom standards. So, Pavi, what are some of the companies that offer this type of home internet based on fiber? Can you,
Uh, TBB,
yeah, 3BB, for example. Okay. Any other brand?
AIS,
AIS? Yeah, certainly, right? Even through internet also, no? Uh, And also TOT, they also provide the service based on fiber as well. Yeah. So these days, the trends, they move from the telephone line based to optical based internet, right? But when we talk about the optical fiber communication, it's not only about for the home internet, right? But there are some other types as well. Can you guess what type of where would the fiber optical fibers are used besides for home internet? Can you give example, Pavi? Or can you guess where else besides home internet are fibers used?
uh, can I question again?
Yeah, the question is, when we talk about optical fiber communication, these days we not only talk about home internet, but there are also other systems that employ optical fibers as well. Can you maybe share some example? Thirarat, you can share also. Thananpat, you can share as well, no? If you want. What other systems that also employs optical fibers besides home internet? Thirarat, can you have any example?
Example? Um, or satellite.
No. Satellite will be in wireless system. Yeah. Okay. Can you guess where else optical fibers are used besides for home internet? Okay, fine. I'll give you example. It's fine. One is called cellular backbone. Okay. So each cellular tower, it has to carry a lot of data, right? So in order to carry the data from the cellular tower to the switching office, it goes by optics. Okay, so that's one way. Another place where optical fiber is used is we can call it mm, international backbone. Okay, let's say we have to send data, from Thailand to Facebook regional server in Singapore, for example. You know, then it goes by the underwater underwater backbone, meaning that under the ocean, for example. Where else is optical fiber used? It's also used by the electric company as well. Yeah, electric company, they also transmit a lot of their own data through optical fibers. In fact, before 3BB or AIS or through internet or TOT, they start to enter the optical fiber industry. The power generating authority, the power company, is the first company that lays the optical fibers around the country. Okay, next one is the wireless system. This part, there are so many examples as you can see here. One is in the aviation industry. They are used for communication, they're used for navigation for airplanes, they're used for surveillance of the airplanes. Then there are satellite communication, mobile or cellular system, different standard, Wi-Fi, WiMAX, blah, blah, blah. So many vehicular communication system, especially for the driverless cars in the future. This is one of the very main focus for 5G and 6G, for example. You talk about rail signaling. In the old days, the signaling or control signals for high-speed train or for the underground train, for example, they are based on the wire line. But these days, they are based on new standard. They are based on wireless standard like GSMR, for example. Some of them even use the Wi-Fi frequencies for rail signaling, like in BTS, MRT, for example. Okay. And then there are some ultra wideband communication, indoor terahertz tracking system, even brain communication and molecular communication as well. Meaning that all these systems, there are no wires. You just transmit through the airs, you transmit through the space, you transmit through the cells, like communication between cells in your body, for example, it's transmit not through air, it transmit through your body, right? And then the last one is related to data storage. This is so important because you have a lot of data these days. So where are you going to store all this data? Every time you click your Facebook on your Instagram, it has to be stored somewhere, right? So at the end of the day, unfortunately, around the world, only two types of technologies that are the mainstream standard. One is in hard disk drives, where in which Thailand is one of the major manufacturers in the world. Another type is flash memories, for solid state drives and so on. Okay, and then in some of maybe still exists but not so much these days, CD, DVD, and in the future the storage through DNA. So all these systems, they require knowledge in digital communication system, and believe it or not, they employ some similar blocks as we shall see. Okay, so what is the simple block diagram for digital communication system in general? So we look at you have input data, then you have to do format, meaning change the data. They can be voice, they can be image, they can be videos. You convert it into binary data. It can be binary, it can be non-binary. Okay. When we talk about binary, it means we have data 0 or 1. When we talk about non-binary, it means we convert data to 0, 1 all the way to m-1 type of pulses. Okay, and then we start to frame it. Framing meaning that we put all this data into frame. Maybe you have some overhead somewhere. This depends on the standard from the previous page. You put overhead and then you have data, and then possibly you have parity bits at the end. Okay, so it's quite standard everywhere for all the communication standard. Okay, then from here you modulate, meaning that you convert from data to pulses. Okay, and then you transmit to go to the channel depending on what communication system we are talking about. So on the receive side, okay, so maybe when you transmit here, you have something like this. So you have something like this. It's just an example. Okay, but on the receive side, maybe you have all this like noisy and then some distortion and so on. Okay, so in a way, we still transmit semi-analog form, because we can, when we say we transmit data like data bits, we cannot just send bits, we have to send pulses, right? So in a way it's a semi-analog, but we embed the digital data inside. And then from here, what do we have? Sometimes we have some circuit here called detector, okay, and then followed by A to D, which is sampler, okay. So from at this point we have a discrete system, okay, and then we make decision whether they are uh, one of these bits or one of these symbols, okay, and then reverse the process. So that's how the digital system works, okay. You have any question? If you have any question, feel free to interrupt me, no problem, okay. So let's talk about some of these blocks as an example. So when we talk about formatting, what do we mean? We mean that depending on the types of data, let's say you enter text data in your line program or in your Telegram program, for example. When you enter the text data, it has to be translated or converted into some types of bits, right? And a very popular type of format is called ASCII. Okay, here is a 7-bit ASCII. So if you type in like this is an example, So these are the 7 bits for the alphabets that you type in. Okay, let's say that you type in, say, Thirarat. What is your nickname? Is it C? Thirarat Pavi. What is your nickname?
My nickname is Nine.
Nine. How do you say in English? Is it
Nine.
Nine? Okay. Let's say you type. Oh, nine is number 9, right? Oh.
Yes.
Okay. Let's say you type 9 into your line program. So what it does is it has to convert each alphabet into the bits. Okay. So if you type in N, it will convert to 100. Okay. 1110. Okay. But you see that here it's 7 bits, right? It's not 8 bits. Normally we have to convert to 8 bits. So we will leave 1 bit here for, we call it parity. Okay. Parity. And then followed by I. So here, this is I. So the program will convert I into 1001001. Okay. So notice that here you type in, I put in the capitalized letter, right? If you type in the lowercase letter like N-I-N-E, the ASCII letters will be different. Okay. And then here we leave the parity bit as well. Okay. Depending on whether it's odd parity or even parity, for example. Okay. And so on for N and E, Okay. So, okay, Pavi, remember this number, okay? I will give example from on the next page when we talk about parity. Okay, so what is the parity? You can imagine that for parity, there are 2 types, either even parity or odd parity. Okay. I think the description is on the next page, but let me say it anyway. If you talk about even parity, it means here you will, let me change the color to maybe blue color. Okay. So if we talk about even parity, it means we will add either 1 or 0 here. Okay. At these bits, so that the total number of ones in here becomes even number. Okay, so let's say I talk about even parity. Here I will add, what should I add, Pavi?
uh,
Here we have 4 ones already, right? We have 4 ones. Okay. If I look at even parity, at this spot, I will add either 0 or 1, which makes the total number of ones in the block, in the byte, to become even number. Okay. But you can see that it's already even, right? Because there are 4 ones. Is that right? There are already 4 ones. So what do we add here at the end? 0 or 1?
0.
Yeah, we add 0. Okay. On the other hand, if you look at the 7 ASCII bits that represent I, okay, if I talk about even parity, you can see that here there are how many ones?
T.
3 already. So here we have to add what?
1.
Yes, exactly. And then the total becomes 8-bit or 1 bytes, right? So here it becomes 1 byte. And this is how it works for ASCII. Okay, this is for text. Okay, it keeps doing that. Okay, so let's go to the next page. We talk about parity bits. So for text, text mean, text messages. We normally add 1 bit parity to check if the errors occur. So for parity bits, the task is for error checking only, no correction. Okay, it cannot correct. It can only check. Okay, no correction. Why? Because from the previous page, is 100,110, right? Wait, 100, 110. And then 110, right? And then we add 0, right? Per V. So when we transmit this data, from the transmit side, this mean transmit, no? X and then mem IT. X mean trans. Okay. And then on the receive side, we never know what is transmitted, right? So if on the receive side you receive something like this, 100,110,000, for example, on the receive side, so we ask question, are there any errors here? Let's say we talk about even parity. Okay. On the receive side, we don't know what is transmitted anyway. Otherwise, we don't need to transmit, right? But for even parity, it counts number of ones. It says, oh, number of 1 is 3. But it's even parity, so something is wrong. So there must be errors. Okay. So parity is used for error checking, but you cannot tell which one is wrong because it doesn't give that such capability. Okay. So for 1 bit parity, either even parity, odd parity, or even parity. So we add 0 or 1 so that the sum in terms of XOR or modulo 2 on the entire block is 1. Okay. Or equivalently, we add the parity bit so that the number of ones in the block is odd number. Okay. For even parity, similarly, we add 0 or 1 at the parity bit so that the sum in terms of mod 2 or XOR on the entire block becomes zeros, or equivalently, so that the number of ones in the whole block becomes even numbers. Okay. And what do we mean when we say XOR? Well, if XOR is represented by plus and then circle, So if you have 1 plus 1 plus 1 plus 1 like this, if you have odd number of 1, you get 1. If we have only even number of 1, we get 0. So this is the XOR. Okay. So I don't need to give any more example, no, because an example has already been made on the previous page. Okay. I can go a bit quicker here. Okay. Next page. Let me skip. Okay. I gave example already. Okay. Next, let's talk about images or videos. Okay. So in this case, if we have images, normally images has 3 components color, which is red, green, and blue. We call one single unit called of the image as pixel. Okay. So what's the flow of converting an image into bits? Basically, an image is we look at each pixels. We need to see how many pixels are there, and then for each pixels, how many bits is represented by the how many bits represent the pixel. Okay, so for an image, for example, let's say we have one color. I mean, if one color of R, G, and B, each component color, let's say is represent the 8 bits. So one pixel contains 3 base colors. You can call base colors, no? Same thing. BASECOLOR, base colors. So if one base color is represented by 8 bits, so when we have 3 colors, it represented by 8 times 3, which is 24 bits. Okay. And then how many colors are there? Well, if each pixel is represented by 24 bits, the total number of color is 224 colors. Okay. So sometimes this is called resolution as well. Okay. So the more resolution, the better, the more colors you have. Okay. So in general, so to compute number of bits for image, we look at number of pixel and then multiply by number of bits per pixel. Okay. Let's see. I have any example here? Let me see. Okay. Maybe on the next page, no. Okay. Also on image, normally we have number of rows and number of columns to represent an image. Okay. Okay, for video similarly, videos contains how many images or how many frame per second, right? For videos, can you guess, Thirarat, how can you guess how many frames out there in a second for video? Video is just a set of images, right? That play so that you feel like they are continuous.
Um, I'm not sure.
Okay. Just guess. Yeah. Guess. How many images does it have to play for each second so that we feel like, oh, it's moving? One?
One.
One actually a bit too small. Uh, the typical number that we see is 20 to 30 frames per second. Okay. Frame FPS. Okay. If you only see one per second, then it doesn't seem like movie. No, it seems more like a images, one image, two image, three image for each second, no? But in normal standard is about 15, let's say 15, 20 to 30 frame per second, okay? Or in any way, it means that in each second, you have 20 to 30 images, right? And then to compute the bits, you convert the how many images into pixels and then how many into bits, okay? So for videos, this is the computation. Number of bits for video is first, you need to look at how many seconds you're looking at, how many frame per second. Normally is about 20 to 30 frame per second, right? Multiplied by number of pixels per frame. Frame here is actually just image that we are looking at, no? But for video, they often call frame. And then how many bits per pixel. That's all. Okay. So let's look at an example in this case. Okay. Okay. An example is, let's say that we want to convert the following information into bits. Okay. Let's see. There are two cases, one and A and B. Okay. For A, we want to convert an image with a resolution of 100 by 100, and each pixel is described by 12 bits, or each color is represented by 4 bits. Okay. So 4 times 3 becomes 12. Okay. For part B, we want to compute the number of bits of videos of 20 frames per second for 10 seconds, and let's say that we have the number of pixels according to part A. Okay. Okay. So let's work on A first, no? So okay. So part A, let's compute number of bits. Part B, how many pixels are there for part A?
12 bits.
How many pixels? Pixels. How many pixels are there?
Pixel.
Here. Yeah. So it's an image with 100 rows and 100 columns. No. 100 rows and then 100 columns. Okay. Okay. So how many pixels are there? Mhm. Oh. Okay, when we say 100 by 100, it means we have 100 rows in the image multiplied with 100 columns. So number of bits here is, let me erase some of this strange line. Okay, so here the number of bits is equal to 100 times 100. These are the total pixels. Okay, number of pixels of this image. And each pixel represented by 12 bits. Okay. So we have what is it? 12 and then 40, right? Okay. Okay, which is 120 kilobits. Okay. Okay, next one. Tirarat, let's look at next one. For part B, we want to look at the number of bits in the videos. Number of bits in a video. How many seconds are there? Tirarat?
10 seconds.
Okay.
Okay.
So we have 10
So we have
seconds.
10 seconds.
Okay. Multiply with
Okay,
how many
multiply with how
frames
many frames
per second?
per second?
20.
Okay, so 20 frame per second,
second,
and then multiply
then
with
multiply with
for each
for
frame, which
each
is
frame, which is
an image,
an image.
right? We can use the result from part A. Okay, so I'm gonna write. Let me write it like this: 1.2 times 10 to the what? 4 or 5? 5, no? Okay, that's all. So here we have 200, or 2 times 10 cubed, multiply 1.2 times 10 to the 5. Okay. Yeah, I don't know why they always line like this. Okay. Well, this is 1.2. Okay. And what is it equal to? Oh, this is 10 second. Eh? Why do I have 10 cube here? 10 times 20 is 200, right? 200. Okay. So what do we have here, Tirarat?
24 multiplied 10 to the power of 6.
Yes.
Yes.
Or you can just do 2.4 times 10 to the 7. No, that's fine as well, right? Okay. So, but you're right. You know, if you put in terms of 6 is better, because we it's easier to say, you know. Oh, one moment. So it's 24 megabits, right? Yes. Okay. So let's say in 1 second, so in 10 seconds, you have to transmit this type of videos, right? You have 10 seconds for transmission. Oh, it depends. You have 10 seconds of videos, but let's say you want to transmit within 1 minute, within 1 second. Okay. So what is the speed you have to transmit per V? You have 10 seconds of videos, but let's say you want to transmit it through your mobile phone within 1 second. What's the speed we are talking about? Pavi? Mhm. Are you there?
Yes. Yes.
Yes. If I want to transmit 24 megabits within 1 second, what is the required data rate? What's the required speed? 24 megabits only transmit to, say, your mobile phone in 1 second. What is the speed we are talking about? No idea, Pavi? How many bits per second? If you want to transmit 24 megabits in 1 second, what is data rate?
2.4.
Eh? Well,
2.4. I'm not sure for this.
well, you want to transmit 24 megabits in 1 second. If you want to transmit in 1 second, the speed is just 24 megabit per second. Okay. Okay.
Okay.
But if you want to transmit within, let's say you want to uh, to transmit with your mobile phone in, let's say, 5 seconds, then what is the speed now? Can you try, Pavi? If you want to transmit 24 megabits within 5 seconds, what is the data rate? Data rate has the unit bit per second, no? Right? Okay. Are you listening to me?
Yes.
If you transmit in 5 seconds, you get 24 megabits. How many megabits per second? How do you compute?
To 24 megabit per second.
No. In 5 seconds, not in 1 second.
In 5 seconds,
If you transmit the total data in 1 second, yes, the speed is 24 megabit per second.
maybe 120.
No, I think you don't understand my question. Yeah, my question is, what's the data rate if you transmit this amount of data within 5 seconds? If it takes 5 seconds to transmit 24 megabits, what is the data rate per second? Is 24 megabits divided by 5, because the unit of data rate is bit per second. Okay. You don't understand my question or what?
Yes. Now I understand.
Yeah, it's like if you want to travel with the speed, you are okay. 2 hours you can travel with 100 kilometers. Or 2 hours you travel, you get 100 kilometers. So my question is, what is the speed in kilometer per hour? You understand what I'm saying now?
Yes.
So it's 100 divided by 2, which is 50. Okay. So same thing. So here you get 4.8 megabit per second. Okay. So if you want to transmit a lot of data within a short time, then you need high speed of your system. Okay. If it takes longer time, then you have lower speed. That's what I'm saying. So for images, for videos, you always need to transmit much faster. Okay. Tirarat, I have a question for you. So do you think in real life when we transmit videos, do we transmit the all the data, or we have some ways to reduce the amount of data?
We have a way to reduce the amount of data.
Yeah, exactly. Have you heard of the standard called MPEG? Like MPEG 4, MPEG 5, Have you heard of it? Yeah.
Yes.
Yeah, there's a standard to compress videos so that, the amount of bits becomes smaller, and then uh, you can transmit more data, but not all the entire bits, But then you can recover the videos. Okay. 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 Next page. Let's see. Okay. This is probably about the example I gave earlier. Okay. And I show it this already to you, no? So normally when we frame data, it means we have to put data into blocks. Sometimes we can call frame as well, depending on the standard. Okay. you have data here, you have overhead, sometimes we call preamble, and then we have parity at the back. Okay. The parity does not need to be 1 bit, no, depending on the standard. But for the ASCII bits, that one it has 1 bit for parity. But when we put all the text together in a bigger frame, normally we have additional parity as well. Okay. And the data can be binary, can be non-binary, no problem. Okay. So where are we in this class compared to your ISO OSI network architecture model? Okay. So normally for ISO model in data network, you have 7 layers. Okay. And so what are the layers, you transmit? In this class, we are here at the physical layers. Okay. We transmit data with the different connection. Okay. And it has to be put into the frame with the overhead. Okay. But when you want to really transmit this data to represent something else or to different network, okay. So basically, for each layer, you add in more overhead. Okay. So here it means you add more overhead to your original data. Okay. And typically we're talking about 30 to 50% of overhead on top of your data to be transmitted. Okay. So originally, from physical layer, if you have data already and you have some overhead here and then CRC. Okay. When you go to the next layers, you add in even more overhead and so on. So a lot of overhead. Okay. 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 Shall we continue? You want to have a little break, small break, 5 minutes?
Yes.
Okay. Tidarat, you want a break, small break?
Yes.
Okay. Let's have
Okay,
a
let's
5-minute
have a
break.
5
No,
minute.
not so long. Okay. Okay. And we'll come back. Okay, are you back yet?
Yes.
Okay. So on this page, I think you have you seen this page before, Thirarat or Pavi, the ISO model? Okay. So if you have question or you're interested, basically, uh, for ISO model, okay, this is different from the IP model. For ISO model, we talk about different layers. Different layers. In some ways, it means you add more and more overhead. Let's say you have some of this data from the physical layer, and uh, then when you transmit through data link, let's say you use Ethernet, Wi-Fi, or some other standard fiber channel, there will be address that you have to add in the overhead. Okay. And then from here to here, then what type of protocol, network protocol are you trying to use? If you use IP or IPsec, you have more overhead here. And then from here, you want to transport. Transport means you have to send it to some place. If you use TCP, which is very common, you send your data packets and you get like a confirmation return. But if you do UDP is like a web-based type protocol. I mean, it doesn't have to be web, but I mean, it's similar to like the web type protocol. You broadcast your data, but you don't get confirmation whether the users receive the packets or not. Then you have to specify what type of transport protocol. And then there are some information. The next layer is related to session. When you to establish session, because every time you send something, you need to start the session and you end the session. You can think of when you try to do telnet or you try to log in or you try to use like remote desktop somewhere. Then you have to start the session and then you finish, something like that. And then on top of here, for the presentation, it's related to the type of data representation, encryption. It can be your Word document, it can be your JPEG data, MP3 files, or HTML web page and all that, And on top of that, it's called application layer. So for ISO model, you have like a 7 layers, but when people talk about IP model, maybe you talk about only 3 or 4 layers, not all of these. So it depends on the model that you're looking at. But in this class, basically we are at the bottom here, roughly at the physical layer in this class. I know that in this semester, you're also taking the data network class, right? And that will be the rest of the layers. Okay. So when we talk about sending data or modulation scheme for digital system, one of the most basic modulation scheme is called pulse amplitude modulation. Okay. You can sort of guess that this is a modulation scheme that modulate the amplitude. Let me change color to red. Okay. So you can sort of guess that we modulate depending on the amplitude. Okay. So here, what does it do? Basically, we let's say we have data bits. We have AI which represent data bits, and the value can be either 0 or 1. Okay. This is for the binary system. And then we map to amplitude from 0 to 1 into -1 and 1. Okay. And for each value, we convert this. We convert from AI into BI, which selects the amplitude from -1 and 1, and then we modulate it on the. We modulate this amplitude onto the pulse. We call modulation pulse or GT. Okay. Let's say, as an example, this is an example, no? The pulse that you use is a square pulse with amplitude A, and the bit time is TB. Okay. So the data that you transmit, the series of pulse is called MT. Okay. Okay. So for binary case, we have BI is equal to 2AI minus 1, it, which convert from 0 and 1 into -1 and 1. Okay. And for non-binary case, so for non-binary case, you have AI in 0, 1 all the way to m-1. Okay. And then we convert to BI for non-binary. We convert from AI to BI using the formula 2 times AI minus m-1. Okay. For example, let's say that AI is equal to, let's say is 0. Let's say, sometimes we call this as MRE signaling. Okay. Okay. Let's say M is equal to 4, meaning that there are 4 levels or 4 symbols we transmit. So AI comes from 0, 1 all the way to 3. Okay. Let's say AI is equal to 0, 3, 2, 1 or 2 to 1 that we want to send. Okay. So we will convert using the formula BI is equal to 2 times AI minus m-1, which is -3. Okay. So basically this operation of AI to BI is to convert the positive amplitude into half positive and half negative. Okay. So BI will be equal to what? 2 times AI minus 3. Okay. First one is 2 times 0 minus 3. Pavi, what is 2 times 0 minus 3?
Negative T.
Yes, -3. How about 2 times 3 minus 3?
T.
3. Yes. How about 2? 2 times 2 minus 3?
1.
Yes. And the last one is 2 times 1 minus 3 is -1. Okay. So basically, this formula, what it does is that if you have AI, which consists of 4 level of amplitudes, if 0, then 3, and then 2, and then 2, and then 1. Okay. It translates this 0, 3, 2, 1. Okay. Basically, it converts this into positive and negative equally. Okay. so that when we mod on the pulse, we have positive and negative. So that's all it does. So for 0, so this is 0, 3, 2, 2, 1. Then we have what? -3, -1, 1, 3. Okay, this is BI. So we convert to -3 and then +3 +1 and then -1. Okay. Okay. Actually, they're discrete, but I draw it as the continuous signals. Okay. So actually, this BI, this is after you multiply with GT. Okay. If the amplitude of GT is A, then you have 3A, 1A, -1, -3. Okay. 3A, 1A, -A, -3, depending on what A is, okay, in the system. Okay. So let's look at an example on the next page. Okay. Were you able to follow on the last page? Was it okay? You have any questions?
Okay.
Okay. Okay. If you have any question, don't hesitate to interject. No. Okay. Also, basic parameter is like this. If when you transmit each bit with the bit duration of TB. Okay. Then the bit rate is 1/TB second. Okay. Let's say also you can write it like this. Let's say you have n bits. So you transmit with n bits, but each bit consists of TB second. So total of n bits is NTB. Okay. Let's say you have n bits. Okay. So you have 1/TB. Okay. So you can compute the data rate by knowing TB directly. Okay. So this is for the binary type system. Okay. That for each bit, it has a TB. Let's say this is bit 1. Let's say this is bit 0. Okay. So you can convert this TB directly into the data rate. Similarly, okay, let's look at an example then. See, I have any other example? Okay. Let's look at this first. Okay, let's look at first example. Let's say we want to transmit 5 bits, 10110. Okay. So part A, write an expression for MT and draw the results of the signals that you transmit. Second, computer bit energy, and C, computer data rate. Okay. So I think B and C, we did it we have done it last time, no? But let's do A first. So this is G, is a rectangular pulse. You know, normally for rectangular pulse, rect T/TB, this is from last time, is the pulse like this with the width, with the duration TB, okay? And multiply with A, okay? A amplitude. But here, because it's shifted to the right by TB/2, so you notice that in here, in this formula, we put T minus TB/2 here. Okay. Just to signify that it's shifted to the right by half a bit. Okay. So let's look at part A. Part A, we want to write an expression of MT. MT is the total data that we transmit. and draw the result. Okay. Let's look at part A. So this is part A. So MT, because the modulation pulse is just a square pulse. Okay. So for binary, we convert this into BI first, and we get 1 minus 1, 1, 1 minus 1. Okay. And then we multiply each amplitude to the square pulse. Okay. So we get the square pulse A minus A, and then plus A, and then minus A. Okay. You can draw this together. I'm not very good at drawing, so this is what I see. Okay. So this is MT, the series of data pulses that are transmitted. Okay. And if you need to write it out, we write it as MT is equal to summation of BI multiply with GT, where in this case, I is equal to 0 to 4. Okay. You can put I is equal to 1 to 5 as well. Okay. But here I write it like this. Okay. And should I expand or not? I don't think I'm going to expand. I'm just going to keep it like this. But I will put rectangular pulse in here so that it looks a bit more formal. Divided by TB. Okay. Of course, if you expand it, you will get 5 terms. Okay. If you expand it, you get 5 terms. Okay. But there's no need, no. I just want to show how to write it anyway. Okay. Okay. For next part B, let's not do it, no, because we did it during last lecture. Part B, it asks about the bit energy, right? Energy per bit. Oh, maybe I should. Energy per bit. Okay, part B, because there are 2 types of data bits. If it's bit 1, we transmit with this. Oops. If it's bit 1, we transmit with A, like this, right? If it's bit 0, we transmit with the negative amplitude, minus A TB. Okay. Thirarat, last time, what is the bit energy for the top one? And then how we prepare for the next one. Mhm. You just square the amplitude and
1.
and integrate. Mhm. What do you get when you square A?
A square.
Exactly. And then when you integrate, meaning that finding the area under A square in the period of TB. So you get A square TB. Always don't forget the square, okay? Not always. Okay. Pavi, how about E0, energy of bit 0? What is the energy? What do you get when you square minus A? Mr. Pavi?
Yes.
What do you get when you square minus a square? Minus a, when you square it, what do you get?
A square.
Exactly. So actually it's the same, right? It has the same energy. You get a square TB. Okay. So if we transmit bit 1 and bit 0 with equal probability, meaning that, we transmit 0 and 1 with about probability of 0.5, okay, we get the average energy like this. Average energy per bit is equal to EB is equal to E1 plus E0 over 2. And what do we get? Tirarat?
1/2.
Yes, multiply with
multiply with
E1 plus
1 plus
E0.
E0.
No, it's the
Mm.
same
It's the
value,
same
right?
value, right?
You add them
You
together,
add
you
them
get
together,
twice
you get twice
the value.
the
2a
value.
2a
Yes.
squared
Yes.
TB.
Yep. And then divided by 2, right? So this is like the average energy per bit divided by 2, which is a square TB. Okay. Okay. On the other hand, if I say that, okay, let's do C later. C is very short, no? If probability of bit 1 or bit 0 is 1/4, probability of bit 1 is 3/4. Okay. In this case, we cannot just add this and divide it by 2. We have to do this. An average energy per bit, or EB, is equal to 1/4 time energy of bit. Oh, sorry. Because they are equal, maybe I can do it. That's fine. But let me show in a detail, no? So we have to write 1/4 times a square TB plus 3/4 times a square TB. Okay. Okay. But because the same term, no? So in this case, you get a square TB as well. Okay. But if they have different energy, this is how you have to compute. Okay. Okay, and part C, what's the speed? Oh, this one is easy. Just say RB is equal to 1/TB bit per second. Okay. Okay. Next, there's a next one. It's a repeat. Okay. It's a repeat, no? From the previous page. Okay. Okay, let's skip this one, no? Okay. Okay. So we looked at the very simple modulation scheme called PAM, which is pulse amplitude modulation. How about the channels? The communication channel actually represent the physical medium in which the pulses of data are sent through. They can be twisted wire pair, they can be wireless channel where you transmit through air, transmit through the atmosphere of the earth. It can be optical fibers, it can be electrical wire, for example. Okay. An example is the twisted wire pair that you use for transmit, like on the Ethernet, Ethernet or landline as an example. And the different types, basically they consist of these wires in here, and they normally comes in pairs, and they have some type of insulation outside, and then inside is the copper. Okay, they always come in two pair to represent like one direction, forward direction and reverse direction of data transmission. Okay, if you look in on these pictures, you will see that they come in pair and they twisted. That's why we call twisted pair. Okay, and maybe there are 4 pairs here, so here you have 4 pairs as well. Okay, there are different types. For example, they call UTP, STP, and for STP, basically you put more shield outside. The reason we normally put a lot of shield outside, so that each pair does not interfere with each other, or they don't induce the pair nearby. Okay, so in order to reduce the interference. Okay, and outside there's another shield. This is normally a very hard plastic or hard shield outside. Okay, but we often call it sheath. Okay, so this type of twisted wire pair, they use in different Ethernet standard. Okay, for example, for Ethernet or landline, we talk about different categories. The higher categories, it means you have higher bandwidth of the wires. Okay, let's say for 5E, for example, is based on the UTP wires here. Okay, and the bandwidth is 100 megahertz. But application it is used is 100 or 1000 base T. So if the bandwidth is 100 megahertz, it doesn't mean that we can only transmit 100 megabit per second. It can transmit all the way to 1 gigabit per second, for example. Or if you look at Cat6, it's also based on UTP, and it has 250 megahertz bandwidth, but you can transmit 10 gigabit per sec Ethernet, and so on. Okay. So on this picture down here, this is an example of we call it insertion loss per 100 meters for Cat5e. Okay. So in this system, on the x-axis, you see that this is the frequency or the supporting frequency, the bandwidth in essence. Okay. So depending on for Cat5e, the bandwidth is 100 megahertz here. See, so at this 100 megahertz, which is about this point, you get the insertion loss of minus 20 decibel per 100 meters. Okay. Of course, if you transmit at 1000 megahertz, here you have the loss of minus 80 decibel per 100 meter. Okay. So when the Cat5e cable, when it comes out, the optimal point, originally it was used as 100 megahertz. So normally the landline, is not going to be so long. It will be like 100 meters or less anyway. Okay. If you use for 200, let's say you use 200 meter, then you get minus 40 decibel loss in your signal. Okay. But anyway, later when people expand the data rate, they transmit with higher frequency on Cat5e, but they transmit with not just binary, but they transmit with non-binary system. So you get more data. So on this side, this is like a data rate. It's different. It's separate from the bandwidth, no? Okay. So on this side is the data rate for data, but here is the bandwidth of the cables. Is the bandwidth of the twisted wire pair. In a way, you can say is the channel bandwidth separate. Okay. And another type is called coaxial cable. So for coaxial cable is typically also used for high frequency, high data rate. Okay, like RG29, RG6. Okay. Here it has a conductor in here which is copper in, and then there are insulator, and then shield, and then plastic jacket. This is like the cable for like the CCTV, or for high frequency or RF like satellite or high frequency signals. An example of connector is N type like this. So this is the connector. This is different from the landline. The landline, it has like a plastic where you just plug into your computer, or you can just plug into to some port behind your computer, for example. Okay. And this part I will come back a bit later. Not today. Okay. So for wireless type, there are different type of channels. This is the wireless channels. If at low frequency, we can look at ground wave, sky wave, satellite, and also just the typical air. Ground wave, we talk about using frequency of the radio signal, radio frequency below 3 megahertz. You can transmit parallel to the earth like this. We call ground wave. Okay. Distance is about 100 to 150 kilometers is okay. Okay. If you go from about 3 megahertz to about 30 megahertz or less, you get a sky wave. Sky wave is you transmit from one place, and then it reflects the ionosphere to other parts of the world, and then bounce from the earth, goes back to the ionosphere, and then bounce to the earth. Normally we call multiple hops of transmission. This height is about 250 to 300 kilometers from earth. Okay. And next one is satellite. Satellite, you transmit and receive from satellite. It depends on what band you use. If you use C-band, you transmit with the 7 gigahertz and 4 gigahertz. This is called uplink and downlink. Okay. They use different frequencies in order to separate the frequency, to reduce the interference and so on. Okay. Next one is the KU band. KU band is at higher frequency, 14, 11, and then Ka band at 30 and 20 gigahertz. Okay. For system like the Starlink, by Elon Musk and all that, I guess they use KU band and Ka band. Maybe mostly KU band. Okay. But because it goes through the air, it's susceptible to rain, attenuation, and all that. Okay. And another one is called for airplanes. Normally they utilize the VHF. This is for communication. They utilize the VHF band above the FM at 108.75 megahertz all the way to 136 megahertz. And it communicates between the airplanes and the towers, the airport towers, for example. So, you have different frequency band that we utilize in communication. Okay. So this is a picture of the different bands that we use. Okay. We can use, from even kilohertz all the way to megahertz, that covers, AM, amateur radio, HF. It goes all the way to mobile, VHF TV, and so on, and all the way up here. Okay. So on the right hand side here, this is frequency. But on the left hand side, sometimes for very high frequency, we describe using wavelength instead, or lambda. Okay. So for high frequency, like for optical fibers, free space optical communication, we use lambda instead to describe the frequency. We don't use frequency, we use wavelength when it's very high frequency. Okay. And if you talk about like new technology like mobile communication, depending on the standard that you're looking at, but let me see, do I have any of this? Let's say up from in 2G we have GSM, no? And then for 3G and up plus we use a standard so-called 3GPP. And there are like a CDMA 2000, they have like a WCDMA and so on. Okay. For starting from 3G, they use a 3GPP standard, but for different version, we call release number, like different numbers of release. Okay. And nowadays we have all the way to release, actually not 15, 16, but already release 17. Okay. So all here, this is still 3G all the way to release number actually around here. Sorry, it's the 3G. Okay. And then from release 8, 9, 10, 11, 13, 14, we call 4G or LTE. Okay. And starting from release 15, 16, 17, we call 5G. Okay. You see that for different release, the data rate start to increase higher and higher and higher. And the supporting channel bandwidth also need to increase as well. When you go to LTE, for example, the data rate, release 8, 9 goes all the way to 100 megabit per second. And then for the last version of 4G, it's specified up to 1.2 gigabit per second for downlink. The arrow like this means downlink. Okay. So in the past, downlink is the speed is higher than uplink. But these days starting to be different, no? Because we start to broadcast data, so the uplink is equally important. And then for 5G, you see that the standard specify all the way up to 20 gigabit per second. Okay. And in here you see this type of standard related to all these different release. For example, if you look at release 8, 9, they use the 20 megahertz bandwidth. Only one channel is okay. They use the antenna called MIMO, or to transmit antenna to receive antenna. Down here, we're not talking about this yet. It's the after midterm. It's that modulation scheme that they require, and they use binary with M is equal to 64. Okay. When you go to standard like 11 and 12, you see that they use the 20 megahertz, but they use two two bands. Then when you look at the release 11, they use 3 bands. Okay. Then for LTE Pro or release 13, 14, you see that they use the they use 5 channels, meaning you can use less, but the standard allow you to use 5 channels. That's why you see the news that many of these companies they auction more and more bandwidth, for themselves. And then it also supports all the way up to 4 transmit antenna and 4 receive antenna. And because of very high data rate, so M for the non-binary is all the way to 56 and so on. And then for 5G release 15, 16, they support many antennas for transmit and receive, and they still use non-binary modulation with M equals to 1024, meaning that each pulse represents 10 bits. Okay. It also supports millimeter wave all the way to like about 20 plus gigahertz frequency. Okay. And then it supports the low delay application, like for robots, for factory robots and all that. Okay. This is also very important. Okay. Different equipment that we use in the standard, they will specify the user equipment or UE. Okay. And there are different categories. Okay. Some categories support very low speed. This is downlink speed, and this is uplink speed, depending on what release of 3GPP you're looking at. Okay. So in here, I only put up to release 12 and 13 in order to understand some terminology or some vocabularies. So like for example, your mobile phone, you know, your mobile phone, for example, the higher speed you have, generally the higher category you have. And for different category, it support different number of antenna as well. Okay. But in later release, like 12 and 13 forward, we start to, some of the user equipment also support this category called M1 and NB1 or category 0. You notice that this release support like a very low speed. Can you guess what type of application this is? Thirarat, can you guess what type of application that requires low speed rather than high speed? If you just download data or gaming, you need high speed, no? Generally. But in some application, we don't need high speed.
Communication.
That's very generic. Everything is communication. Yeah. Actually, this type of low data rate, they exist even in 3G or 2G already. Yeah. Have you seen like the ATM machine? They have like a small antenna on top. Or in the supermarket, every time when you swipe the credit card at the cashier, they have to communicate in some way to the center, right? These devices are all based on wireless system. Okay. In the past, they call like a M2M, like machine to machine communication, or they call M2M. Okay, like the machine device, small device talk to the device. No, not for us to talk, but the device talks to each other. All right. So this require very low speed. They already exist since 2G, but then in 3G, 4G, they specify this data type very specifically because they want to support these IoT devices. Okay. So in later release, they focus on IoT. Like for example, you talk about like sensors that monitors temperature or monitors some environmental monitoring. Maybe you monitor, you have some data once every second, so not so high speed, right? You can put SIM card in there and transmit to the cellular tower as well, like in LoRa standard or uh, in NB-IoT, standard like LoRa, NB-IoT, something like that. Yeah. So you transmit data very low speed through the cellular system, but generally, like in 5G, 4G, 5G, we support a lot of them, but each of them has low speed. Okay. So it's different from the data that we download or upload, like on Facebook or YouTube and all that. Those you need high speed. Okay. Okay. Uh, okay. An advantage of digital communication is to vary data rate. Okay. Last time in the lecture, you noticed that we have an expression that uh, analog SNR, which is PS over PN, is equal to digital SNR multiplied with the spectral efficiency, or the digital SNR is equal to analog SNR multiplied with 1 over spectral efficiency. Okay, and this is W over RB. Okay, this is from last time. So in digital communication system, whether they are like Wi-Fi, they are satellite, they can vary the speed. They can vary the speed in order to increase or decrease digital SNR, which is EB over N0. Okay. For example, if you talk about satellite system, if the rain gets heavier and heavier, it means the analog SNR becomes lower. So we have to increase the digital SNR. What we do is we reduce the data rate. Okay. So we reduce data rate lower and lower so that we can keep the quality. But of course, when we reduce the data rate, it means your TV signals, your videos will have a lower resolution, just to accommodate connection. You can talk about Wi-Fi when you are away from the router more and more. Then you have lower power signal or lower you have lower SNR. In order to increase the digital SNR, you will have to reduce the data rate as well. Okay. So very similar in all systems, the same. No. Okay. This is probably one of the last one of the introduction slide. I don't think I can. I think we are one lecture delay, no, but it's okay. We will go slow, but I think you start to see overall picture. This slide is also very important. Please make the star here. Okay. This day, because most of the communication in digital system is all about data. Okay, even your voice is transmit through the IP packets. So everything is data. It can be voice, it can be data. So this day we divide the service or data type. We we specify the quality depending on the service, the type of service for the data. Okay. For example, if the service of this data is for conversational voice, like when you talk online, like talk or messenger, telephone call, for example, uh, the the classifier of this class is called QC1. QCI is level 1. Okay. Q represent QoS. Pavi, do you know what QoS is?
No.
Okay. I should ask Pio. Pio, you are in here, right? Pio? Are you still in here, Pio? I think you are here, but you disappear. Pio, are you there? Okay. How about Hirarat? You know what QoS stands for? Can you guess?
Yes.
Quality.
Yes, it's
Yes,
quality of
quality of
service.
si-
service.
Yeah,
Yes.
service. It means that when we specify the data depending on the type of service, if the service is for voice, we have to guarantee this type of QoS. This is called QoS. Okay. For voice, what are the type of quality we have to maintain? Let's talk about these three. One is priority, meaning that how urgent is this type of data guaranteed. Then we talk about delay, and then error loss rate. In a way, it's like packet error rate. No, same thing. So if the data service is voice, then the system will guarantee the priority number 2, not number 1. No, the delay can be not more than 100 millisecond, and the error rate cannot be more than 10 negative 2, meaning that out of 100 packets, on average, the error is less than 1 packet. Okay. If we talk about QCI2, this is live streaming. Like if you stream using Facebook or YouTube, and so on, it guarantees priority number 4. Packet delay is less than 100 millisecond, and the error rate is 1 out of 1,000 packets, or 10 negative 3. Okay. And what else? Yeah. Real-time gaming. Real-time gaming, if you play games with real-time interaction, this will be the priority is number 3, but the delay is much smaller because it's a real-time interactive gaming, right? 50 millisecond and 10 negative 3. Okay. V2X. Thirarat, can you guess what V2X is?
Two-way message.
No, this
No.
is maybe not easy, but put a star here. It's called vehicle or vehicular to anything. Okay. It's a standard of communication between your vehicle and anything. For example, from one vehicle to the another vehicle, or from one car to the sensor along the highway, or a car communication from one car to the sensor billboard above the highway, for example. Okay. So they specify this type of service specifically called V2X. You can see the delay is very low. Packet error rate no need to be so low. Okay. Another place, if you look in here, which is also V2X, is this. Also low delay, not so low error rate, because V2X, they have different types of data. Okay, depending on what data in V2X. Okay. And anyway, and the last one I talk about is this one. This is called buffered streaming. Like YouTube video, you watch like a video, YouTube videos that has been uploaded by someone. So the delay no need to be so small, 300 millisecond, priority number 5. And but then for videos, generally the error rate has to be very low. Okay. The reason I put star in here, because when you go into the industry, and if the people industry, they ask about different service of your data, different QCI, this table is what they expect that student in telecom industry understand. Okay. Last one, this is IMS signaling. This is the system signaling in the system to check the quality and all that. It has the priority number 1. Okay. The error rate also has to be small, and the delay only 100 millisecond. Okay. There are also many other types of service like email, FTP, and so on. No, you can take a look at it. Okay. Okay. This page is very large, a lot of details. No, if you have question, please ask me. And here, maybe I pass this first. No need to go with it now. For these slides, I go very small, very quick. This is history of digital communication. The start of the modern digital communication is 1924, when Nyquist explained about the sampling theorem for band limited channels. Okay. Another year that is important is 1948 by Shannon. He came up with the theory called information theory, which indicate the highest, the maximum data rate through AWGN channels. Okay. But then in 1948, here he specified the technique to reach maximum data rate, and the technique that introduced is called error correction code. Error correction code, okay, which is the type of code that is different from parity check code, that you can correct errors on the receiver. Okay, so from that time on, people talk about these different techniques for ECC. This is also ECC, ECC, ECC as well. That improves the data rate in the system. Okay. Quantum communication comes into 1985. The modulation scheme called OFDM. This one comes very 1960, 1970. Okay. MIMO communication together with OFDM. For practical OFDM, it comes in 2005. Okay. 5G comes in 2020. 6G planning comes into 2021. Okay. And actually, I forget to put in here about 2016-17, brain communication, meaning communication through brains, already started. No. So in 6G, the theme is called deep communication. And the concept is think and send. Okay. So in 6G, we will start to have a sensor that when you think about something, you can transmit right away. You don't need to type on your mobile phone. But 6G won't come out until 6-7 years from now. Okay. So it will be a while before you see 6G coming. Okay. I think that's the last slide on introduction. So we finish introduction now. Okay. Okay. You need another short break before we come back to look at Simulink. Pavi Thirarat Thanan Pat.
Yes.
Okay, let's have a five or 10 minutes break. A 10 minutes break, okay? Because for Simulink, I don't think that today there will be